let's discuss PointNet in a bit more detail. One idea of PointNet is to use the symmetric functions as we discussed before. For example, maximum and sum are two functions that can take in a set of points and that give the same result regardless of the order of the points. So if x2 and xn switch positions, then the max function still gives the same results if it is computed dimension-wise, that is component-wise, as we discussed before. Let's also go over basic PointNet or vanilla PointNet again. And let's look at this building block here that is a function h that goes from Rd to Rd prime. For example, the input dimensions are d equals 3 and the output dimensions are d prime equals 1024. This function h takes a single point as input and it outputs a point that has 1024 dimensions, or it outputs a feature for this point that is a 2024 dimensional features. And this function is modeled by a multi-layer perceptron, a network with linear layers. Before, we actually looked at each of the outputs component-wise, so instead of writing one function h, you could also look at each output component. That means there could be d prime different functions hi to break it down even more. But since we already did that before, it should be clear now what this function h does. So now let's go back and ask what is the function f that vanilla PointNet computes given a set of points as input. And so now we go way to the right. And so for each point x1, we separately compute, for each point xi, we separately compute this function h. So this point x1 will be sent through the MLP, and then hxi outputs a 1024 dimensional vector, feature vector for this point x1. Every point will have to go through the same procedure, all go through the MLP, and then finally also the last point here goes through the same MLP. All the weights are shared among all the points. That is an important part. And so also the last point xn will be transformed into a 1024 dimensional feature vector. Now the symmetric function comes into play, and there will be a maximum computed dimension-wise for all the 1024 dimensional features. So the output of all of this is going to be a single 1024 dimensional feature. So the max basically transforms n, the number of points, times 1024 scalar values into a single vector that consists of 1024 scalar values. Then there is some post-process that is conducted by the function gamma. The function gamma operates on this one feature vector that basically describes the whole point set now. So what can we do to process a 1024 dimensional vector? Well, we'll simply use another MLP. So gamma is a function from d prime dimensions to d prime prime dimensions. So the complete PointNet function f is now a symmetric function, and it is permutation invariant. Let's look at a figure. Here we have a visualization of the point set consisting of k unordered points. This seems to be notation from the paper, so let's replace that with n, which is what I used, and also let's replace that with n, since we used n before. Now, each of these points, for example P2, will be processed by a multilayer perceptron. Again, this multilayer perceptron only gets P2, that means 3 scalar values as input, and it outputs a vector that has 1024 dimensions. But of course this is a hyperparameter that can be changed. And all of these MLPs share weights. That's why it says here the weights are shared. Then the maximum will create, out of all these vectors that are output, one single vector here that then will be further processed by this MLP to give a final output that is one vector for the complete point set. The paper also offers some analysis of what can this function f actually represent. The idea of the analysis is to show that a function can be approximated arbitrarily well. There are always some conditions, so the authors say that a Hausdorff continuous symmetric function f can be approximated arbitrarily well by PointNet. That means that the difference between f x1, x2, x up to xn, that would be an arbitrary function of the given function class, minus whatever PointNet functions we have in the PointNet function class. So the difference between these two functions, that means the best fitting functions, can be made to be smaller, equal to epsilon for all points. For the details, please refer to the PointNet paper. The other component that the authors propose is a spatial transformer. A spatial transformer takes an arbitrary input point cloud and tries to align it somehow. So this is a bit unclear what that means. So let's maybe imagine that all of our points are some bicycles, or all our point clouds are some bicycles. And this spatial transformer might have the goal to align all the bicycles in a canonical way. So always that the upside is maybe oriented along the z-axis, that the front of the bike is always approximately in the same place, that the bike is always aligned with one of the axes, and this can help the network to process the point clouds better. So the inspirational goal for these spatial transformer networks is to take any input point cloud and to put it into some canonical coordinate system. At least you give the network the possibility to do so. It's not necessarily that this is what the network does, but what you do is you try to find an output, rotation, and translation that lets the network orient the point cloud in any way it wants. So we said that we want to align the point cloud in a canonical space. So the input now is a set of points, and we have n points, and each of the points has d dimensions. Now this type of alignment works in low-dimensional, three-dimensional space, but it also works in high-dimensional, d-dimensional, 1024-dimensional space, for example. And a network, a spatial transformer, outputs a transform matrix of size d times d, and then the whole point cloud will be aligned by this transformation matrix, and this can be done computing x times t. Studying either computer vision or computer graphics, you might be more familiar with the notation that a transformation matrix T is applied to a single point x. And then there's some output, which is a transform point x prime. But now, if you want to transform a whole set of points, then you have this notation, maybe T times x, where each column of the matrix X has a point. So there's a point here, there's another point here, here, and so on, up to here. And this can be reversed. So if you transpose everything and you don't want to have points in columns but in rows, then this whole thing becomes X times T, where this T matrix is the same as that, except it gets to be transposed. Let's look at the explanatory figure of a 2D spatial transformer that hopefully explains the concept of what such a transformer network might do. In column A, we see the input to a 2D spatial transformer, and this 2D spatial transformer tries to find a region it wants to focus on, and then it performs a transformation so that it tries to align the number that it finds with a canonical coordinate system so that the number is pointing kind of upwards nicely. So for example, for this 7, the spatial transformer detects that this should be the region it wants to focus on, and it doesn't rotate a lot. So if you look at the output C, it's mainly assumed inversion of the input shown in A here. For the 5 in the second row, we see that the transformer detects that also there's some rotation that happened that it wants to undo, and then the spatial transformer zooms into the 5, but it also, maybe you say rotation, maybe shear, it will output this 5 here. And then in the last row, we see there's some other stuff here as well, but the spatial transformer still manages to zoom into the 6. Maybe this fit is a bit less tight than for the other 2 rows, and then again it outputs the 6 as shown here in column C. So a spatial transformer in this example was used as a pre-process for digit recognition. And then what you see in D is the output of a digit classification network that tries to predict what number is shown in the image. So in 3D, we have whole point clouds that are kind of translated and rotated. Of course, an arbitrary transformation can be a bit more than just translation and rotation, but I think it's helpful to envision a translation and rotation as a possible type of transformation. Now, let us also discuss some advantages of this PointNet architecture. First, it can handle an arbitrary number of points in a single data sample. There might be some slight question mark to that. If you give it really an arbitrary number of points, does the network really generalize? We'll just leave that as an open question. If you use the sum as a symmetric function, does it really generalize? Well, maybe you need to use at least the average instead of the sum. Also, basic PointNet modules can be stacked. We will PointNet can be used in multiple applications. For example, classification of a complete point set or segmentation of a point set. PointNet can be used as a backbone for whatever, so it can be used as a point cloud feature extraction network. Similar to other transfer learning ideas with images, you might think about transfer learning ideas with a point cloud network. Let's go over the architecture figure that the authors created. As input, we have a set of points, and we have n points, and each has 3 dimensions. Again, this could change, but we look at one particular version here. Then we have a spatial transformer. The spatial transformer is a black box here that is explained in more detail down here, where the point cloud goes into this one network that learns a 3x3 transformation matrix and applies this 3x3 transformation matrix to the whole point cloud using the matrix multiplication. So as output, you get another point cloud where each of the points has been transformed by this multiplication matrix, by this transformation matrix. So as output, we get this transformed point cloud, and we still have n points. Each point has 3 dimensions. They're just located somewhere else in space now. So next step, vanilla PointNet is operating on each of the points. The points go through this MLP. So these numbers 64, 64, these are the number of dimensions that are output by the individual layers. So what you might want to do is consider this MLP together with this MLP to see the progression of the dimensions in the that are basically output by the different linear layers. So we start kind of with 3 dimensions as input, then we have 64, then 64 here, and then over there again 64, and then it grows to 128 and 1024. But this whole MLP here is broken up by yet another spatial transformer block in the middle here, where again the network aligns all the points, and this time the alignment is done with a 64 by 64 dimensional matrix. If you would delete these 2 blocks, the input transform over here and the feature transform over here, then you would obtain this network as we discussed in the previous slides. So after this second MLP, we obtain a point cloud where each point has now 1024 dimensions. That means there's a 1024 dimensional feature attached to each point. then this will be reduced by max pooling to a single 1024 dimensional feature, and this is a global feature describing the complete point cloud. This global feature is then processed, also as discussed before, by another MLP that now does not increase the dimensions but successively removes it. So the outputs of the intermediate layers are 512 dimensions, 256 dimensions, and then k dimensions. Well, why k dimensions? Maybe we have a classification problem that has k different classes. Then maybe we want to have k different output scores. And what the number of classes k is depends on the particular dataset. But what happens if we're actually not interested in classification, but in segmentation? This figure here actually shows two different PointNet architectures, one for classification and one for segmentation. You can do both maybe at the same time, but let's say you want to do either or. If you don't want to do segmentation, then you don't have this yellow part on the bottom here, so you don't need the segmentation network. And if you do segmentation, then maybe you want to forget about this part here. All right, so now we're interested in segmentation. We have this global feature, and what we're going to do is we'll take this global feature and we append it to each point that is created by the point network at this point in time. So we'll take this point cloud that is created by this block that has or that is basically represented by this block. This is the output of this feature transform. That is a point cloud where each point is described by 64 dimensional features. And we append these 64 dimensional features for each point with the global feature. So now each point has 1088 dimensional features attached to it, but each point has a unique 64 dimensional feature that comes from the purple part above, so that comes from here, and then it has a shared global feature that comes from here. So what I draw here in red is unique for each point, and let's pick some other color. All right, that failed big time. So this is unique, and let's see if I can switch the color. Then this part is shared. So this is the same for every point. All right, so then this point cloud again goes through some MLP. And then some other MLP, and then as output we have n cross m, where m should be the number of classes that we are trying to predict with the segmentation network. Let's look at some results. On the left, we see some difficult partial inputs where partial objects are fed into PointNet for segmentation, and on the right, we have the regular segmentation where complete objects are given to PointNet. Let's just look at the right side. So what we can see here is that the segmentation does not have a lot of details, and it's a very coarse segmentation. For example, the bag, there are two classes. One is the handle, and then the other one is the main part of the bag. Or the skateboard, we have wheels, 4 wheels, and we have the main part of the board in a slightly different shade of green. Or the earphone is segmented into 3 different classes where we have 2 regions of the yellow class. this is part segmentation because one object is broken down into individual parts. A unique characteristic of this is that the parts are kind of stuck together, and one has to find a dividing line to kind of cut an object into individual parts. In a different setting, that is like a scene segmentation, then often there's a lot less connectivity between the individual parts and that we want to segment out, and the individual parts are actually individual objects, and they might be much less connected to each other. They're mainly connected to the floor. So here we see some scans of real rooms, and I think for the part segmentation, this is a synthetic data set, but this one here, this is a real scanned data set where there are real scans acquired by a scanner. And so we see the input on top, and we see the segmentation on the bottom. What we can see is that in general, the chairs are nicely segmented out, and also the tables are nicely segmented. This concludes our history lesson of the initial point cloud processing paper. And the nice thing about it is that really the mindset that people back then had was, we just want to get some results. And I think this was really a milestone where this was the network that got a lot of attention for having the first significant results. Of course, there was other work, but somehow this network is known to be this first significant paper in the topic. But of course, now things progressed very rapidly, and the current networks are a lot more sophisticated and also have significantly higher performance. Still, this network is something that can be completely understood from the paper or even this presentation, I hope, and this is something that can be implemented from scratch. For other networks, implementing from scratch becomes a lot more challenging. And we will go over these other networks with using a bit less detail, so we'll mainly explain high-level concepts.